Okay, we will solve another problem. This time we will have a beam and the truss, and we will try to calculate the deformation of that structure. So I have a beam here and I'm supporting it from the top with the truss member. The length of the truss is 2 meters and length of the beam is 3 meters. And this one is also 3 meters. So total length is 6 meters. I have a uniformly distributed load on this beam whose magnitude is 3 kilonewton per meter. And let's put a note that that's a beam. And I want to calculate the deflections or determine the deformed shape of this structure. So for simplicity, we will say that, I mean, it's given like that. The EA truss is equal to EI beam in magnitude. Okay, so that's the problem. So we know that since that's a beam, we don't have to worry about the axial deformations. And you can actually see that because it's under the transverse loading only. So there's no axial force on it. So we will only think about the bending deformation. Now I have a truss, so by definition it undergoes only the axial deformation. And take a look at it. This, I have a hinge here, so the moments are 0 at both ends, and I don't have any loading on this truss member, so meaning that this truss member doesn't have any shear on it, doesn't have any moment. It can only carry axial force. So in order to do that, first let's do the discretization. Let's see how many members we have, what are the degrees of freedoms that I want to use to calculate the deformations. So I have a node at this top of the truss, another node at the intersection between the beam members. I have a beam member here and another beam member here, another node and another node. So basically I got 1, 2, 3, 4 nodes, and I got 3 members. Let's try to figure out the degrees of freedom. I'll go node by node and determine the degrees of freedom. Now the first node, I have a pin support, so I have only rotational degrees of freedom. That's D1 for me. Now I go to the intersection of the beam and truss members. It can move in the upward direction, that's D2, and it can rotate, that's D3, and the end node, it can move in the upward direction, D4, and it can rotate, D5, and here I don't have any degrees of freedom. A truss member is connected to this node, and this node doesn't allow any translation. The other question that you might ask, why didn't we define any horizontal degrees of freedom? Because we know that that's a beam. There's no axial load here, it's just a transverse loading. So we all now know that these horizontal translations are equal to 0. So in this structure, I got 5 degrees of freedom. And also let's show the loads. I have a member load here and another member load here. And let's show the local axis. So I'm defining it this way, that my start node, that's the end node. So that will be the x prime axis for this member. That will be the y prime. This is the local axis of my first member. Let's say that that's the second member. and I define it from left to right, and according to this definition, this is its local x-axis, that's the local y-axis, and I'm defining the truss member. Remember that here I'm showing the directions of the local axis, so that's the x prime, that will be the y prime for the truss member, and this is my, let's say that, third member. So in this discrete version of the structure, I show everything that I need, the degrees of freedoms, I have the members, and here I show their local axis. Remember that we will use these local axes while defining the deformations. And let's remember the governing equations. So for axial load or axial deformation, we derive the following. Axial force on a member is equal to E times L divided by L multiplied by the deformation. And for the bending deformation, we have a differential equation which is equal to d square y, y being the transverse displacement, is equal to m over ei. And in order to solve this axial deformation equation, I only need to know the axial force, and that's it. But in order to solve the second order differential equation, I have to know the moments, and I need to know two boundary conditions. That's the only way I can solve this equation. Okay, now the next step, I have to calculate the forces on the members, and for that I will be drawing the free body diagram. So let's draw the free body diagram. Again, we will be using the discrete version, the members and nodes. So I'm showing everything here. And that's it. Now, let's try to calculate the forces. I have a support reaction here. Let's give some labels so that it will be easier for us. This point A, point B, C, and D. Now I have a vertical reaction, AY here, and I have another vertical reaction, that is dy. Okay? Now I'm taking moment with respect to that point. Okay? I have to show the uniform distributed load also, sorry for that. Yeah, we have these uniform distributed load, 3 kilonewton per meter and 3 kilonewton per meter. Now I'm taking moment with respect to that point. The moment created by this uniform distributed load is 3 by 3 times 1.5. It's in this direction. And the moment created by this uniform load is again 3 by 3 multiplied by 1.5, and it's in the opposite direction. So if you sum up these two moments, they will cancel each other. So the system is already in equilibrium. So this tells me that AY is equal to 0. So if AY is equal to 0, then dy should be equal to 18 kilonewtons. And these are all the support reactions. So let's transfer this 18 kilonewton to the member. So this truss member is under tension, and the magnitude of the load is 18 kilonewtons. And I got this on this member, 18 kilonewtons. Now I'm writing the equilibrium equation for this member. So this force is 9 kilonewtons, and the moment at this end is equal to 13.5 kilonewton meters, and on the other side again I have 9 kilonewton shear force here, and the moment is again 13.5 kilonewton meters. And if I transfer them to the nodes, I got 9. I have to erase this, sorry for that. Let me redraw the free body diagram of this one more time. This moment. Okay. Alright, now we have this 13 kilonewton moment. Now I'll redraw the node one more time. So from the truss, I got 18 in the upward direction, and from the beams, I got 9 in the downward direction, 9 in the downward direction, and I got these two moments that cancel each other. Now, after that, we see that this node is in equilibrium. So now the whole structure is in equilibrium. Let's draw the moment and the axial force diagram, because for the axial deformations, I need the axial force diagram, and for the bending, I need the moment diagram. So let's show the sign convention. This is plus. These are my positive directions. That's the sign convention. Okay. Now, while drawing the force diagrams, so axial force diagram, and I have the moment diagram. Now I have to be careful, so the directions that I choose for these members here should be exactly the same in these diagrams, so that we'll have the same definitions at every member. That's something that we have to be very careful. So I will draw it. This is the truss member, that's the beam member. That's our structure. So the truss, in the discretization, we define it from bottom to top, and for the beams we describe it as from left to right, left to right. Now the axial force, I got tension, and the magnitude of the tensile force is 18 kilonewtons, so it's positive. So I got positive plus 18 kilonewtons, and this is the axial force that I have. Now let's draw the moment diagram. So I know that the moment is equal to 0 in here. Now the directions are like that, and when we go from left to right, that's the positive direction, and here I got a negative moment. So here I got a negative moment here, and the magnitude of that moment is 13.5, and at the beginning of this member it's equal to 0. Let's take a look at the second member, and it's also negative here and 0 at the other end. So this is 0. Now what about the variation? So we know that that's a uniform distributed load, so the variation of the moment will be a quadratic parabola. It's 0 here, and the shear is also 0, meaning that the slope of that parabola should be 0 here, and it should keep increasing in the reverse direction, because this is also a negative moment, so the slope should increase and reach to 9, and the moment that we will see will have this form. Okay, let me also plot the shear forces here. Now let's take a look at the second member. We start with the negative 13.5. Now I have a positive shear force. This is and zero shear force here. So I should have the highest slope at the beginning, and the slope should decrease as I go to the end of the member. And since this is a positive moment, the moment should increase as I go in this direction. So the shape of the moment for the second member is as follows, and this is minus. Now, what about the equations? Now, while writing the equations, I should use this is my x prime, and for the second member, this is the origin, that will be the x prime. And in order to determine the moment, equation for the moment, you can take a section cut here. So I take a section cut, there's no shear force, that's the moment, and the magnitude of that is equal to 3 kilonewton meters, and the equation of that for this moment diagram is m of x prime is equal to minus 1.5 x squared. And you do the same thing, take this member, I have now a shear force here 9 kilonewtons, a moment here 13.5 kilonewtons, uniform distributed load. I'm trying to write the equation for this moment. This is for the second member, and when you do that for the second member, we obtain m of x prime as equal to minus 13.5 plus 9x minus 1.5 x squared. So if you look at this, we need all the information that we need, right? I have the axial force, I have the equations for the moments. Okay, so I know this, I know that. Now the next question is, what about the boundary conditions? So how should I start? If I start from the first member and try to solve this differential equations, there's only one boundary condition that I know, which is the vertical translation is equal to 0. So I cannot use this or start from this member. If I start from the second member, it's even worse because there are 4 unknowns. I don't know any of the boundary conditions, any of the displacement boundary conditions. If I start from the third member, I can use this equation that will give me the elongation on this member, which would be equal to d2. So if I start from the third, I can determine d2. If I know d2, I can jump to the first member, because now I know d2, there are 2 unknowns, and I know 2 boundary conditions. So I can actually solve this differential equation and determine the values of d1 and d3. So once I determine the value of d3, I can jump to the second member. I know 2 boundary conditions in that case, and I can calculate what d4 and d5 is. So that would be my solution approach. I'll start from the third member, determine d2, go to the first member, determine d1 and d3, and then second member, determine d4 and d5. So I have all the information that I need. I know where to start and how to solve this structure. So let's do that. Now we said that I'll start from member 1. Sorry, the truss member 3 in that case. So I'll just draw this member this way. This is the top node, this is the bottom node, right? And I will show also D2 here, and I got D3 here. Now we have a tensile force on this member. The tensile force will create an elongation whose magnitude is delta. And from the axial deformation equation, I know that 18 kilonewtons is equal to EA divided by length. Length is 2 meters multiplied by delta. That's the axial deformation equation, and from that I obtain delta as equal to 36 divided by EA, or I can just write it as 36 divided by EI. We said that we have the same magnitude in here. So that's equal to 36 divided by EI. Now, according to this deformation, that's in the downward direction, this elongation. But our degrees of freedom say that the positive degrees of the displacement is in the upward direction. So according to this, d2 is equal to minus delta. So my d2 is equal to minus 36 divided by EI. So I determine the value of the first degrees of freedom. Why negative? Again, let's take a look at this degrees of freedom. According to my definition here, I assume that the positive direction for d2 is in the plus y direction, okay? If it moves in the upward direction, d2 would be positive. But as you can guess, this truss member is under tension and it moves in the downward direction. So that's why d2 should be negative, and that's the way we determine it. Now let's take a look at the first member, right? Let's draw it. I have a pin support here. That's our first member, and that's not. Let's show the degrees of freedoms. I got d1 here, I got d2 here, and d3 here, and we already calculated the value of d2 as minus 36 divided by EI. Okay, now let's write the boundary conditions. So at x is equal to 0, I got y is equal to 0. That's my first boundary condition. And the second boundary condition is at x is equal to 3, y is equal to minus 36 over EI. Let me show what x and y is. I no longer use primes. Okay, that's the local axis. That's x and y. Okay. Now we can write the differential equation for bending deformations. d square y divided by dx square is equal to the equation of moment, which is equal to minus 1.5 times x squared divided by EI. If I integrate that once, I obtain the equation for the slopes. dy over dx is equal to minus 1.5 x cubed divided by 3ei plus c1. Integrate this equation one more time. I obtain y as equal to minus 1.5 x to the power 4 divided by 12ei plus c1x plus c2. So in order to determine the values of these constants, I have to put the boundary conditions in. So first boundary condition is x is equal to 0, y is equal to 0. So that should tell me that c2 should be equal to 0. The second boundary condition, at x is equal to 3, y should be equal to minus 36 over EI. So if you put x as equal to 3, I got minus 1.5, 3 to the power 4 divided by 12 EI plus 3C1 should be equal to 0. And from that equation, we obtain C1 as equal to minus 8.625 divided by EI. So let's calculate the slopes now. So we determine the equations. So let's calculate the slopes. So at x is equal to 0, dy over dx will be equal to this value minus 8.625 divided by EI, and at x is equal to 3, dy over dx is equal to minus 22.125 over EI. And let's plot the deform shape. So what I did here is I just used this equation, put x is equal to 0, 3, and obtain this value. So let's plot it, okay? So here we see a deformation, 0 translation, but we have a clockwise rotation. So this is a clockwise rotation, and the magnitude of that rotation is 8.625 divided by EI. And we know that this point moved in the downward direction. The magnitude is 36 over EI, okay? And the slope is again in the clockwise direction, but it is larger. So let's draw it in an exaggerated way. And the magnitude is 22.125 divided by EI. So the deformed shape of that member will look like this. Okay, now we are done with the first member. Now I know that now the D3 is equal to the slope at this point, so it's clockwise, and our positive direction is counterclockwise. So D3 will then become equal to minus 22.125 divided by EI. Now I determine, if you go back to our discrete structure, now I determine the value of D2 and D3. And again, if I repeat the same procedure, I can obtain the values of D4 and D5. So let's do that. So I will be using this space for it. Now I'll write the same equations, the same approach, use the same approach for the second member. That's the start node of that member. This is my second member. That's the end node. That's the direction that I choose. So this will give me the x direction as follows. And this is the y direction. Now let's show the degrees of freedoms. I got D2 and D3. I got D4 and D5 here. So the boundary conditions at x is equal to 0, y is equal to minus 36 over EI, and at x is equal to 0, dy over dx is equal to d3, which is minus 22.125 divided by EI. So these are the boundary conditions, okay? Now let's write the differential equation. Let me use this space for it. So d square y dx square is equal to minus 13.5 divided by EI. I'm writing the moment equation now. Plus 9x divided by EI minus 1.5 x squared divided by EI. I mean, we'll repeat the same procedure. Let's integrate it one more time. dy over dx is equal to minus 13.5x divided by EI plus 9x squared divided by 2EI minus 1.5 x cubed divided by 3EI plus C1, and when you plug this boundary condition into that equation, you see that the C1 will be equal to this rotation value. So I will just write it directly, minus 22.125 divided by EI. That's the equation for the rotation. I will integrate that one more time, and I obtain the equation for the transverse displacement as minus 13.5 x squared divided by 2EI plus 9x cubed divided by 6EI minus 1.5 x to the power 4 divided by 12EI minus 22.125 divided by EI times x. And again, now if I put this boundary condition into that equation, I obtain the second constant as equal to minus 36 over EI. So I'll just write it here, minus 36 divided by EI. And that's the equation for the transverse displacement. Now I need to determine the values of D4 and D5. So you just use these two equations. You just put x as equal to 3. Then we will obtain the rotation as equal to minus 35.625 divided by EI. And at x is equal to 3. Now we will use the second equation. We obtain the transverse displacement as minus 132.745 divided by EI. Okay? Again, let's plot it on this member. So we know that this point moved in the downward direction, and the magnitude of that translation is 36 over EI. But this point moved more, and the magnitude of that translation is 132.745 over EI. What about the slopes? So here, the slope is in the clockwise direction. Magnitude is 22.125 over EI. And at this end, I got a larger slope. So let's show it this way. And the magnitude of that larger slope is 35 over 625 divided by EI. And if we draw it, we see a deformed shape like that. And the value of D4 will be then equal to our positive direction is in the upward. This thing moved in the downward direction, so it is minus 132.745 over EI. And D5 is equal to, is the slope, minus 35.625 over EI. Now, as you see in our solution approach, if we go back to this discrete version of the structure, we isolate every member from each other, okay? Like we did in the free body diagrams. We are isolating it. If we are discussing the deformations, these two isolated members talk each other through nodal degrees of freedoms. So we isolate this member, calculate the degrees of freedoms, D2 and D3, and we are done with it, okay? And then I come to this member, I isolate it as if I have a single member with certain boundary conditions and calculate D4 and D5. That's the main solution approach. As you see, once we discretize it, we did the same thing in the free body diagrams. I isolate that member, write the equilibrium equations only for this member and calculate the end forces. Transfer the end forces to the nodes and transfer from the nodes, transfer to the other member and isolate that member. Write down the equilibrium equations and find the member end forces. So when it comes to forces, the members communicate with each other through member end forces at the nodes. And when we talk about the deformations, again, the members communicates through using these degrees of freedoms. Now we determine all the degrees of freedoms. We know the values of all the degrees of freedoms. Now let's draw the deform shape of the whole structure. So let's do that. Let me use black. So that's the undeformed shape. That's our truss member here. Let's start from this node. What I know about this node is this rotation. And it's in the clockwise direction. And the magnitude of that rotation is 8.625 over EI. We know that this point moved in the downward direction and the magnitude of that translation, the vertical translation, is equal to minus 36 over EI. And this point also moved in the downward direction. Well, I have a larger deflection here and the magnitude of that deflection is 132.745 over EI. Okay, now let's plot the rotations now. The rotation at this end, at where we have the truss member, is calculated as 22 minus 22 over 125. Again, it's in the clockwise direction, so I just exaggerated just a little bit. And I should have the same rotation at both sides of the member. So that's a clockwise rotation, that's a clockwise rotation. And the magnitude of that rotation is 22.125 over EI. And at this end, I got a larger rotation. So let's show it this way. It's again in the clockwise direction. And magnitude is 35.625 over EI. What about the variation in between? Now, for the first member, the variation is described by this equation. It's a fourth order polynomial. And for the second member, the variation is described by this equation. Again, another fourth order polynomial. Of course, I'm not exactly drawing it, I'll just sketch it, but if you are curious how it moves, you can just write these equations in Excel or something and draw the exact deform shape. So I'm just sketching it, so I should have some curve, and this will be something like that. I mean, of course, it should be just a single parabola, but it's difficult to show here. We just sketch it, okay? And as I said, if you are curious, you can just use Excel to calculate it. And this is the final deformed shape of the structure.